this module. You will learn about some important concepts of thermodynamics like heat, internal energy, and work. Consider two thermodynamic systems, say gas A and gas B, which are in two chambers of a thermally insulated wooden box and separated by a metallic partition. Let the initial temperatures of both gases be T1 and T2, with T1 greater than T2. We know that after sufficient time, they attain thermal equilibrium. Basing on this observation, temperature is defined as a thermodynamic variable that is equal for systems in thermal equilibrium. Systems at different temperatures and in thermal contact attain thermal equilibrium because heat flows from a hot system to a cold system. An important point to note about heat is that it is energy in transit. It exists as a flow only. A question like, how much heat does a sample of gas contain, has no meaning. In thermodynamics, the energy possessed by a system is internal energy, usually denoted by U. The internal energy of a system is the macroscopic thermodynamic variable that changes when it either emits or absorbs heat energy. The temperature of a body may or may not change when it absorbs or emits heat energy. But in both cases, the internal energy of the system changes. For example, ice at 0 degrees Celsius converts to water at 0 degrees Celsius by absorbing heat energy. Though there is no change in the temperature, the internal energy of ice increases when it is converted to water. On the other hand, if water at 30 degrees Celsius is heated to water at 60 degrees Celsius, both the temperature and internal energy of water increases. At a microscopic level, the internal energy of a system is defined as the sum of kinetic energies of all its constituent molecules due to their translational, rotational, and vibrational motions, and the potential energies due to the interaction between these molecules. An important point to be noted is that the kinetic energy associated with the motion of the center of mass of the system does not influence its internal energy. Similarly, the internal energy does not include the potential energy due to the interaction of the system with its surroundings. For example, take a system of gas in a container placed at a certain height. If the container is dropped, the kinetic energy of the center of mass of the system increases, but there will be no change in the internal energy of the gas. The gravitational potential energy of the system is greater when it is at a certain height than when it is on the ground. But the internal energy of the system is the same in both cases. Let us now look at another example in our daily lives. We all are familiar with the fact that our hands become warmer when we rub them together. Though there is no external supply of heat energy to the hands, the work done due to the friction between the hands makes them warmer. This implies that the internal energy of the hands, considered in this case as a system, is increased by doing work. That means that by doing work, we can change the internal energy of a system. Let us now consider a mass of gas enclosed in an airtight container with a movable piston as a system. Now compress the gas by exerting an external force on the piston. This can be done by placing some weights on the piston of the container. We can observe rise in the temperature of the gas. When the gas is compressed, the external force due to the weights did some work, and as a result, the internal energy of the gas is increased. That means that when work is done on a system, its internal energy increases. Now, by removing the external force on the piston, if the gas is allowed to expand, the temperature of the gas decreases, indicating a reduction in its internal energy. Hence, when work is done by a system, its internal energy decreases. That means we have two different ways of changing the internal energy of a system. One by allowing the system to exchange heat with its surroundings, and the other by allowing it to do some work. In thermodynamics, heat and work are the two modes of energy transfer to a system. Heat and work are not state variables. They depend on the path through which the system is taken. For example, consider a given mass of gas at an initial state described by P1, V1, T1. Let us plot a pressure versus volume diagram for the gas and identify the initial state of the gas as A in the PV diagram. Let us take the gas to a new or final state, described by P2, V2, T2, and identified by D in the PV diagram. We shall take the system from the initial state A to a final state D in two different ways. In the first method, place the container of gas on a hot reservoir maintained at a constant temperature T2 and allow the gas to expand at constant pressure. After sufficient time, the gas may be at a new state, identified by P1, V1-T2, and represented by point B in the PV graph. The curve AB represents the process of changing the state of the gas from P1, V1, T1 to P1, V1-T2. Now, keeping temperature constant, compress the gas by placing a weight on the piston to the final state P2, V2, T2. This change in the state from P1, V1-T2 to P2, V2, T2 is represented by a curve BD in the PV graph. In the second method, compress the gas by placing some weights on the piston and change the initial state of the gas P1, V1, T1 to a new state represented by P2, V-T1. In the PV graph, the new state is represented by C and the process by the curve AC. Now place the container on the hot reservoir maintained at a constant temperature T2 and allow the gas to expand at constant pressure to reach the final state P2, V2, T2. This process is shown by the curve CD in the PV graph. In this experiment, we have taken the system from its initial state P1, V1, T1 to a final state P2, V2, T2 by two different paths represented by ABD and ACD. Heat exchanged by the system in taking it from A to B and then from B to D. is different from the heat exchanged in taking it from A to C and then from C to D. Even the work done by the system in taking it from A to D through ABD is different from the work done when taking it through ACD. In this aspect, the internal energy is different. Internal energy is a state variable. The internal energy of a system depends only on its state and is independent of the path through which it is taken. For example, in the experiment described earlier, let the internal energy of the system at its initial state P1, V1, T1 be U1 and the final state P2, V2, T2 be U2. Whether the system is taken through ABD or through ACD, the internal energy of the system in its final state remains U2 and is thus independent of the path followed. You have now reached the end of this module. In this module, you learned that temperature is the thermodynamic variable that is equal for systems in thermal equilibrium. Heat is energy in transit. The macroscopic thermodynamic variable of a system that changes when it either emits or absorbs heat energy is its internal energy. Internal energy is equal to total kinetic energy of all molecules due to their translational, rotational and vibrational motions plus potential energy of the molecules associated with intermolecular bonds. We have two different ways of changing the internal energy of a system: heat and work. Heat and work are two modes of energy transfer to a system. Heat and work are not state variables. They depend on the path through which the system is taken. The internal energy of a system depends only on its state and is independent of the path through which it is taken.